All right. Well, welcome everybody. Let's see. That is not working. Yeah, I don't think this is on. Second. All right. Well, welcome everybody. Let's see. That is not working. Okay. There we go. Well, that looks like it's sound. Okay. I don't know why it's not lighting up here. Huh. All right. Well, we're gonna operate like it is working. You all can hear me, right? It's on in the room, I think. Okay, great. Well, welcome again to the first Friday Astronomy event. If you've never attended before, my name is Brian Jackson. I'm a professor in the physics department here at Boise State. Welcome. These are monthly lectures. They happen on the first Friday of every month. It's March 1st, which is the first Friday of March. So we're having this. First Friday of the month, 7:30 p.m. Mountain. Always on the first Friday of the month. Sometimes folks wonder, oh, is it on over the summer? Yes, we have it 12 months a year. So even if the school is closed, we're still having this. It does make it hard to recruit students sometimes. But we have these all year. So if it's the first Friday of the month, 7:30, this event is taking place. They happen on campus. For this semester, we're going to be in this room, but starting in the summer, we're actually going to move to a little bit different space. If you joined us in November for Alex Filippenko's talk, we're going to probably move into that room starting in the summer. So it may be a little bit better seating for this kind of event. But keep your eye open for information about the program this summer. These events are also live streamed. So if for some reason you can't join us in person, you can visit the live stream at boi.st/astrobroncoslive. Or you can use this QR code. This will take you to our YouTube live stream where you can watch the talk live, submit questions over YouTube. And then we have recordings going, I think, back 3 years now of lectures. So you're welcome to watch those past recordings as well. So first Friday, 7:30. Feel free to join us. These events, you probably heard me say a million times, these events are 100% donor supported. Donations from folks like you in the audience pay for us to bring our speakers out, pay for their lodging, pay for their food. And so if this is the kind of programming you enjoy, please consider donating to support the program, boi.st/astrogive, or you can use this QR code. It's about $1,000 an event to fly the person out and put them up for a night or two. So that's where we're at. So consider donating. All right, we're in for a real treat tonight. We have Dr. Lauren McCohen. Okay, good. I tried. From the NASA Jet Propulsion Labs in California. Dr. McCohen has a PhD in planetary science from the Trinity College at Dublin, and a bachelor's in physics with astronomy and space science from University College Dublin. She has a really interesting career. I'll let you all kind of look her up online to see the whole thing. But she's currently serving as a Jet Propulsion Labs postdoctoral fellow. For those of you who are not familiar with JPL, JPL runs almost every planetary science mission you've ever heard of, either originated at JPL or has a strong foothold in JPL. JPL basically originates a lot of NASA's planetary science program. So it's a really amazing place to work. And Dr. McCohen, we're very fortunate to have her here to talk about her research tonight. And so with that, let's welcome Dr. Lauren McCohen.
Should I just hold it? Sorry. Hello, is that better? Can you hear me well? No. I have a very small voice, so maybe I should just hold it up. Okay. Is that okay?
Can you hear? I think it's.
Can you hear me? Okay.
Feel free to hold it up if you
want. Okay. Yeah, just let me know if you can't hear me, and then shout at me. So hi everyone. Thank you so much for having me here today. It's amazing that you all donated for me to come. Thank you so much. I'm really enjoying visiting. So yeah, I'm going to talk to you today about who I am and what I do. As I said, as Brian said, my name is Keown, and I'm going to be talking today about plumes and spiders on Mars, Europa, and in the laboratory. And that the insights that can be gleaned regarding the processes that form them from analog laboratory experiments. So firstly, I'll start with a background on who I am. So I'm an icy planetary geomorphologist, and I'm currently conducting research at JPL. I hail proudly from Dublin, Ireland, where I developed my transdisciplinary background with an undergrad in physics with astronomy and a PhD in planetary science. I also have previous research experience at NASA Ames, the Open University, and the Natural History Museum in London. I also really enjoy teaching, having worked as a professor in planetary sciences at Birkbeck in London. And I also love giving talks like this, meeting new people and sharing my research with others. So overall, what do I do? Well, I'm interested in a multi-pronged approach to understanding icy planetary surface processes, both with and without Earth analogs on Mars and Europa, and a little bit of small bodies as well. And I do this through high-resolution remote sensing imagery and lab analog work. I think the analog work is the most fun part, though, so I hope to showcase a bit about that to you today. Forewarning, there's lots of fun and messy videos. So in my spare time, I also do normal human things, and apart from the usual things many of us enjoy, like traveling, I love exploring my creative passions. So I'm a big Halloween enthusiast, and JPL has a Halloween contest every year, and I take that very seriously. So this is me dressed as Jupiter. And at the time, Jupiter had 80 moon babies. I think Jupiter has since had more moon babies. Oh, am I? Yeah. Okay. Zoomed in on the moons. Okay, yeah. So I enjoy doing that. I painted that myself. I do my own gel nails. That's fun for me. Those are some nails where I did the features that I studied on them. And recently I've discovered pottery, which kind of conflicts with the gel nail hobby because you need to be able to pull the pots. And I'm also a cat mom to the world's cutest cat, Pam. And if anything goes wrong today, I have a reserved slide of just photos of her. So yeah. So now what you really came here to hear about, my research. Until recently, Mars polar science has been my bread and butter, but during my time at JPL, I formed collaborations with people that have led me to other icy surfaces that I'll tell you about later. So I mostly focus on present day Mars, the stuff that you're seeing in this video here, features that you can see changing and growing literally today, which in its own right is really fascinating to me, that we can see changes on the Martian surface literally year in, year out, and with the seasons. So while the planet Mars has undergone drastic shifts in climate regimes, today it's cold and dry, with an atmospheric pressure between 6 and 10 millibars, much lower than on Earth, and daily temperature ranges near the equator are from 293 to 233 Kelvin, so very cold. And the planet's atmosphere consists predominantly of carbon dioxide. And like Earth, Mars has polar ice caps, and it also has a seasonal ice cap of CO2 ice that descends on the surface, which you're seeing here. Because it has the planet has an axial tilt of about 25 degrees. Yeah, this seasonal cap changes in spring from solid ice to gas. And here's some examples of the features that we see on the surface with the high-rise camera on board Mars Reconnaissance Orbiter. Switch to the next slide. Yeah, so as you likely know, there are many surface features on Mars that have Earth analogs. So features that are putatively glacial and periglacial landforms, gullies, and so on. And in understanding their formation, we benefit from decades of in situ measurements of similar features here on Earth that are often formed by water in the liquid or ice phase. But what about when we come across features that are totally unlike anything here on Earth? Generally, such features are active today on Mars, and they grow and extend in some way in a climate that doesn't support ongoing liquid water action. And many of these are timed with the spring sublimation or change from ice to gas of the seasonal CO2 ice cap. So two particular features of intrigue to me have been linear dune gullies, which are the features in the center there. Is this my laser? I don't really need to point. Oh, there we go. Okay. So the linear gullies are featured in the center, and then spiders, which are these strange dendritic features, which I'm going to talk to you lots about today. And yeah, these have been observed with the HiRISE camera on board Mars Reconnaissance Orbiter, which is able to resolve features as small as your kitchen table. So I'll touch on linear gullies briefly now, and then come back to my main love, spiders, in a moment. So linear gullies are often long, sinuous channels that are found on sand dunes on Mars in the southern hemisphere. And for my PhD, I was tasked with investigating their formation process in the lab. So unlike Earth's gullies, they show no sign of typical liquid debris flow assisted mass wasting, such as terminal aprons. Instead, they terminate in one or many of these pits, which are these features seen here at the end of their channels. Lots of arrows pointing to various different types of pits. So we have this main pit here, which is kind of the circular depression at the end of their channel. And we've even seen some high albedo features in the pits, which we think may be pieces of CO2 ice or CO2 ice blocks. And then we have all these little detached pits surrounding them as well. So we don't really have features like this on Earth. They're quite curious. In 2013, my current postdoc supervisor at JPL, Dr. Serena Ginega, my PhD supervisor, Dr. Mary Burke at Trinity, and a big role model of mine in planetary science, Dr. Candy Hansen and others, proposed that they form by sliding CO2 ice blocks that levitate like a hovercraft due to the Leidenfrost effect. The Leidenfrost effect is a physical phenomenon that occurs when a substance comes in contact with a surface that's at that's beyond its boiling or sublimation point. So has anyone seen the dancing water droplets on the pan? Yeah, kind of skittering around the pan, really, really hot pan. It's a very similar effect for CO2 ice, that if you put it on a surface if you even put it on this table here, it would slightly levitate. Those folks proposed that, like these dancing water droplets on a pan, the CO2 ice blocks, when they break off over steepened cornices on the dune in spring, they hit the relatively warm dune slope, and then they hover down the dune slope like a hovercraft, carving these channels and then depositing the levees beside them in their wake. And then eventually they'll come to rest at the dune terminus and sublimate in situ and possibly burrow into the sand to form the pits. So here's a cool video of Candy sliding a CO2 ice block down the dune. I believe they just went to the store and bought CO2 ice blocks to test this process on Earth. Unfortunately, I wasn't there for those tests, but this is the work that sort of motivated my work for my PhD. And they have lots of cool videos. They actually have one where they stuck a duck to the CO2 ice block and slid it down. So that was pretty cool. So the blocks kept on going, carving out channels in their wake. However, there was work to be done on verifying whether blocks would form pits when they got to the terminus under low pressure and temperature Mars-like conditions, and how this process would vary under those conditions, so not on Earth. And at the time, I didn't have access to the planetary simulation chambers that I work with now. So I at least tried to eradicate the humidity that we experience on Earth from the situation. And I built this low humidity chamber that's seen in this diagram here, where I basically evacuated the chamber of water vapor by putting CO2 blocks in there to displace the air and get down to a really low humidity. And then so this was like a fish tank of sand. And then I had a little trap door there, and I placed the CO2 ice blocks on the surface and investigated the morphologies that formed. We found that for coarser grains, that the blocks produce morphologies similar to those of the main pits on Mars. Right about here, where you had these kind of depressions, the the shape of the ice block. They're a bit more rectangular because I had rectangular ice blocks, but you get the gist. And then the burrowing effect excavated levees surrounding them. And then another type were collapse pits. So for the finer grains, the blocks actually burrowed beneath the surface and started just kicking up the granular material. And we got these jets coming out of the surface to form these collapse pits. And then another type were these impact pits, where we think that there was granular clustering in the jets, where you got these clusters that then impacted the surface on return. So in this work, we calculated the volumes eroded per given block dimension, and then we surveyed several sites on Mars. So we measured the pit dimensions on Mars, and then where we could see those high albedo objects, wherever we saw them, we measured those dimensions as well. And we sort of reconciled them with the volumes eroded per given volume CO2 in the lab, and they seemed to match when we did the calculations to scale up to Mars. So that seemed to support that the pits were likely formed by CO2 sublimation, or widened to a degree by CO2 sublimation as proposed. And a surprising outcome of the work was discovering that for the blocks that didn't burrow, for the blocks that sat there, that we got these little channels that developed beneath the block. So this was something that was kind of accidental. I was like, "Ooh, what are these?" Kind of exciting. And then my supervisor at the time led me to discover sand furrows on Mars. So these are similar to the spiders, and this sort of was quite literally the twist or turn that would begin a many year-long obsession for me with one very particular pattern in nature, which is what I'm going to talk to you about for the rest of this talk. So this brings me to spiders, more formally known as araniforms for media sensation reasons that I don't need to elaborate on. So spiders are dendritic or branch negative topography networks of troughs that are found in the Martian South Polar layer deposits. So these regions around the South Pole on Mars. They have a whole range of morphologies seen in this top left-hand panel here. So this is a half spider, these are linear spiders, and these are fat spiders. Lots of different types. And they range in scales from less than 50 meters to greater than 1 kilometer in diameter. So each spring we see these relatively dark fans and spots emanating from their centers. But other than that, for the very large, often radial spiders around the South Pole, we don't see any growth. So recently, though, there's been a detection of these what are called dendritic troughs. So these are features on sand dunes. They're on the intradune material on sand dunes. And sand furrows, which I mentioned earlier as well, they're on sand dunes. So in the lower latitudes. That they form year in, year out, and they're erased seasonally or they grow seasonally. So this raised the question of why are some of them forming today and others are not? Why do we have all of these different morphologies? Could some of these features be representative of seasonal dynamics in a past climate? So yeah. And in order to understand these features, we can map them, we can survey them on Mars, but to really understand their formation process, we require empirical data or direct observations of the process that forms them. So hopefully this video plays. Yes, it is. Okay, so regardless of morphology and activity level, all of the spider-like features that I just told you about are proposed to form by some variant of the Kiefer model, which is what you're seeing happen here. So as the animation shows, this model proposes that in winter, translucent slab ice descends on the surface of Mars, and then in spring, sunlight penetrates that ice, heating the regolith beneath it, and then causing the ice to sublimate from its base. And this causes a pressure buildup, which leads to the ice cracking, and then you get pressurized gas rushing towards the vent, which entrains surface material within the regolith. And carves dendritic pathways and then deposits that material on top of the ice in the form of a plume. And then what you see on top of the ice is the dark fans and spots that I just showed you. And what's left is a network of dendritic troughs converging in a central pit to make up a spider. And as you can see here, this process is proposed to happen year to year. growing the spider at a rate that's not yet been fully quantified. So this was a study that we did during my PhD. We got some nice media coverage on it, which led to, if you Google my name, it comes up with the name of David Bowie's band now. So that's definitely a win. The Spiders from Mars, most of the articles open with that somehow. So in this work, I ran experiments to test the Kiefer model for spiders in the lab and made the first empirical connection between high velocity sublimating CO2 gas and then spider formation under Mars conditions in the Open University Mars Simulation Chamber in the UK, which you're seeing here. So in these experiments, we drilled holes in CO2 ice blocks and then excused, I don't show this photo to my engineer colleagues. This is really hacked together, but it worked. We suspended these CO2 ice blocks from a claw as we lowered the pressure in the chamber. We eventually placed these ice blocks in contact with a bed of granular substrate. So I sort of capitalized on the Leidenfrost effect that I just told you about, because I knew that the block would sublimate when I put it in contact with the room temperature substrate. So these were not exactly replicating the temperatures that we expect where spiders form on Mars, but we really just wanted to see would similar morphologies form when you had pressurized sublimating CO2 gas beneath CO2 ice in contact with mobile material. So in each case, when we did this, a plume was generated, which excavated material from beneath the block to form spider patterns, which we saw when we lifted the block up. So we got lots of different spider patterns depending on the grain size. So it was really exciting. So those are coarser grains and these ones are finer grains. They're more dendritic for the finer grains. So by building digital elevation models of the surface, we could then measure the depth of these features and the surface area they covered. And we found that they were more dendritic and covered more area for finer grains and smaller vents. However, as I said, these experiments were performed at room temperature, which isn't exactly consistent with Mars polar springtime conditions. And we also drilled holes in the center of CO2 blocks rather than having a very conformal CO2 layer on the surface. We also didn't use a solar simulator, simulating direct sunlight on the surface. So as an aside, I think that can I play this? Yeah, I think the real highlight of these types of experiments are the very fun movies and seeing how phase changes can behave really differently under lower pressure than on Earth. So lots of folks have called this the laundry machine. This is what happens when you drop a CO2 ice block into granular material under Mars pressure. And you can see the camera shaking there. This was another accident, but it was pretty cool, and it really showed the geomorphic agency of sublimating CO2 under Mars pressure. This actually kept going. Like you can see that the material is being distributed very violently. Under Earth conditions, the block would just sit there. You might get a few little jets from the side of the block. So that was very cool. It kept going until we got to about -10 degrees Celsius, which is about what we calculate for the temperature for Martian dunes when blocks fall onto them. So it shows how CO2 sublimation can be a highly effective geomorphic agent under Mars conditions, and highlights how we really need experiments like this to understand how planetary surface dynamics work that have no Earth analog. So from these lab experiments, we hypothesized that spiders on Mars have formed around the same time. So i.e. where we had cracks in the seasonal ice all operating at once, that we might observe that spiders with greater distances between them and smaller inferred vent sizes would be more dendritic, so have more branches, because those spiders would be formed by much higher velocity gas. So to test this, we then applied what we learned in the lab to Mars. And we surveyed 3 sites on Mars which had clusters of spiders. So here's some examples of clusters of all different morphologies of spiders. We used their central pits as a proxy for vent size, and we measured these, and then we also measured their full extent as well as the distances between them and their number of branches. So for the spiders with over 1,000 branches, this was really tedious work, but very mindful. These groups follow the trend predicted from lab experiments, as you can see in the plots here, suggesting that they perhaps form contemporaneously or at the same time. But we don't know at what stage yet. We don't know. We don't have the exact age of them yet, but it suggests that they formed around the same time. And along the way, we also detected and named some new spider types. So here's the sunflower spiders. I call these flowing spiders. These are segmented and these are spiky. And I also got to informally name a couple of sites. The first one was named Dublin. That was nice. So we've been to Mars in the present day. I want to break up this talk with a detour to Europa for a minute. So Europa is Jupiter's icy moon, which we'll be headed towards with the Europa Clipper mission in October, hopefully. And there's me with Clipper in its earlier stages. I should get a more recent photo. It's great. I get to go see Clipper at JPL. It's so cool. You can see its development. It's like visiting a relative, you know, seeing how it's getting on. And prior to this year, I was really placing an emphasis on how spiders were like nothing seen on Earth or elsewhere. And a few months into my postdoc at JPL, I was amazed when I discovered the spider on Europa. So this is this feature here, which the Europa folk are calling the spider on Europa. So I'd wanted to find a way to get into Europa research for a while and also to get onto the Europa Clipper team somehow and hear all their talks. And so while chatting with my colleague, who's a Europa expert, he asked me if I'd ever seen the spider on Europa. And in my opinion now, this is a pretty genetic term for the feature, and it could cause confusion because we tend to associate spiders with the features on Mars. But I was most certainly intrigued that in the Galileo solid state imager 20 meter per pixel image, at least, it appears kind of similar in pattern to how some Martian spiders appear in lower resolution images on Mars without their dendritic arms resolved. So I took the fact that it was in a crater called Manannan crater, named after the Irish mythology Son of the Sea, to be a sign that I should research it further. So I did a bit of research on the feature and found that a team of researchers who are now actually my friends at JPL, they had hypothesized that it formed by plume activity from an impact-induced subsurface brine reservoir. So this was pretty cool work. They suggested that it consists of a network of fractures and it formed in a similar way to the spiders on Mars. But spiders on Mars aren't exactly fractures as we went through there. And also, despite keen efforts, the jury's still out on whether plumes do exist on Europa. And I wondered if it might be something else. And so I started to research things like dendritic patterns in ice. So you can imagine my amazement when I discovered these. Has anyone ever seen these? Lake stars? Some people are like, I've never seen them. And then some people are like, yeah, no, I've seen them. They're cool. I don't care. But I'm kind of obsessed with them now. So these are really prevalent on frozen ponds in winter here on Earth. So look out for them. And they look exactly like Martian spiders in pattern, which kind of renders my opening statement on my earlier papers. You know, spiders are unlike anything seen on Earth, pretty moot. So granted, they're certainly an example of the issue of equifinality, where you can have similar morphologies that are arrived at by totally different formation processes. And they're definitely formed by a totally different mechanism to spiders on Mars. So these features form on Earth when snow falls on a lake that's covered by a layer of thin ice. And what happens is the weight of the snow forms holes in the ice, and relatively warm water then flows up through these holes through the slush. And a thermal instability forms because the smaller ice grains melt faster than the bigger ice grains. And then a dendritic pathway is energetically favorable. So the flow of water is marked by dendritic melt channels. And eventually the system freezes again, which preserves this spider-like pattern in the ice. So I wondered if something like this could happen on Europa, albeit under very, very different pressure and temperature regimes. So I let this really nice movie of lake stars in Butterfly Lake, China play while I continue my story. So I posed this idea to my colleague, Jennifer Scully, who was working on mapping Manannan at the time, and this evolved into collaboration. So she's done some morphological analysis of the spider feature of the general Manannan region, which indicates that the radiating arms of the spider don't display structural features and therefore may not be fractures. So together with a cross-disciplinary team of planetary scientists and engineers, we developed a new hypothesis for the formation of Manannan spider based on lake stars on Earth. So I'll just play this little video while I talk. It's an animation. Play. Yeah, there we go. So we suggest that the feature may originate from a process similar to that forming lake stars, where its arms are not fractures, but are dark ice surrounded by frozen impact slurry. So after impact, you get this transient atmosphere forming above the impact site. And then a brine pool forms beneath the surface, and you get impact slurry on the surface. And eventually the ice cracks, allowing liquid water from the brine pool to rush to the surface and spread through the slurry. And then as temperatures and pressures were elevated at this time because of the transient atmosphere from all of the volatiles thrown into the region, and we would also have partial vaporization upon the liquid brine reaching the surface. It could exist as liquid transiently. So in a similar manner to lake stars, we suggest that the water flowed through and melted the slush to form a spider-like pattern, which was preserved as it froze. We suggest that the spider feature has a low relative albedo because of its higher salt concentration, which presumably darkened over time. So, yeah. So admittedly, while on vacation in Breckenridge, saying that I wouldn't bring work on holidays with me, I saw these features for the first time after studying them for a year. So I was so excited. I couldn't not explore them. So my poor husband ended up going out into the lake with me, hacking pieces of ice, and we brought a turkey thermometer out there to try and measure temperatures. I was measuring the features because I wanted to understand the conditions under which they form. So we recorded their scales, branching levels, and the general environmental conditions under which they form. However, we still needed to know if these patterns could form under lower temperature and pressure regimes similar to Europa. So in order to see whether the parameter space surrounding lake star formation explored in the field test extends beyond Earth conditions, we performed experiments where liquid water was flowed through granular ice simulant made by the Europa lander team at JPL to investigate whether lake star patterns developed and to explore the parameter space. So as a first step, the experiments were performed under Earth pressure. We'd like to perform them in a vacuum chamber under much lower pressure eventually, but this was our first step of experiments. But different cold temperature ranges down to about -100 degrees Celsius. So we use this custom designed liquid nitrogen cooling glove box, which has a temperature control within the range of -40 to 0 degrees Celsius by duty cycling liquid nitrogen spray inside. And then we also flash froze simulant in liquid nitrogen baths to get the temperatures that we were trying to explore. And we used this fine spray granular ice simulant, as I said, developed by engineers for testing Europa lander. It was used to test the mechanical properties or test the robustness of robotics for Europa lander. And the team were kind enough to collaborate with me and give me their simulant for my tests. So let me play this video here. So for each trial, a small container was cooled using the liquid nitrogen glove box, and granular ice about 0.5 of a centimeter thick was spread on its base. And this was to simulate a thin frozen ice layer in contact with slush. And I used a wash bottle to place it at the surface and flowed water through the center of the granular ice at a constant rate until a lake star pattern appeared or did not, and the water reached the edge of the simulant. So the volume of water used in each case and the duration of each experiment were noted, as well as the different morphologies that were produced. So we explored different grain sizes, different salt concentrations, and different temperatures of the water that we were flowing and the simulant on the surface. So in each case, we got features similar in pattern, though obviously way smaller in scale to lake stars. Arms developed in all cases, but they were less distinct for salty simulant. So this is the salty simulant at the bottom. And then for the ambient room temperature case, the dendritic arms developed into more branch features than for cases with lower difference in temperature between the water and the ice. And the pattern even formed, though froze very quickly for the flash frozen simulant at about -100 degrees Celsius. So far lower than we'd expect on Earth. So our paper on this is under review at the moment, and I'm really excited to see this work get out there. and hopefully get funding to investigate whether these patterns form under post-impact simulated low pressures. So yeah, so after my brief detour to Europa, I'd like to go back to Mars and finish this talk with what I think is one of the most exciting projects that I've undertaken so far. So you recall that in my previous spider experiments, while they showed that sublimating CO2 gas could generate spider-like patterns, they didn't exactly model the Kiefer model in a very realistic sense. What we needed was to condense a conformal layer of CO2 slab ice on granular simulant, and also to replicate the realistic polar temperature regimes expected for this process on Mars. So I spent about 5 years trying to get funding to do this work, with lots of rejections, gaps, the pandemic in between, until we finally won a NASA Roses grant to support them. So I'm really in my element to have completed phase 1 of them now in the Dusty chamber at JPL. So the Dusty testbed, here it is. Here she is in all her glory. Dusty is a state-of-the-art dirty thermal vacuum chamber, which is capable of simulating Martian and other planetary atmospheric conditions. So Dusty is a backronym. I learned the word backronym recently. I think it's great. It stands for Dirty Under Vacuum Simulation Testbed for Icy Environments. It's 45 centimeters in diameter and 60 centimeters long. And it's capable of simulating temperatures down to minus 200 degrees Celsius and pressures down to 10 to the minus 5 torr. And the interior walls of the chamber consist of liquid nitrogen shrouds. And it also has a liquid nitrogen cooling plate, which you can put samples on. And it's equipped with this Pfeiffer vacuum roughing pump and a turbo pump as well, which can nominally get down to Mars pressure in about 5 minutes. So our most recent experiments set out to firstly investigate whether plumes and spider patterns can be generated when a conformal condensed layer of CO2 is sublimated. And secondly, to explore the parameter space surrounding different spider morphologies to generate hypotheses regarding conditions, local conditions where they form past and present. So in running our chamber, we targeted the regimes identified by our collaborator, Anya Portyankina here. So Anya did some previous experiments where she condensed CO2 in a bigger vacuum chamber in Europe and found that translucent CO2 ice condensed around these temperature and pressure ranges. So we were shooting for those ranges, which was great that was already worked out. So as you can see here, we first grew a translucent layer of slab ice onto the plate and got it to be thicker than anyone had, to my knowledge, before, so about 3 centimeters thick. And this is because the chamber is the right size and we're able to cool very effectively with the cold sky. So the shroud in the chamber creates a cold atmosphere. So if you're condensing CO2 on the surface and you don't have a cold atmosphere, it's just going to sublimate like while you're condensing it. So it's a bit of a race to keep growing it. So this chamber is really great for those conditions. We then moved on to growing ice on glass spheres and Mars Mojave simulant dust. So we have some great simulants at JPL, I used less than 150 micron in size MMS dust. So to do this effectively with a thick layer of granular material, we needed the material to be cool throughout. So a shout out to our engineer colleagues who suggested this little cryopod, which is, it's used to cool tools to cryogenic temperatures. So this was a really nice example of cross collaboration where engineers can help us come up with cool ideas for our work based on their experience. It's essentially a little lunchbox size liquid nitrogen bath. And so we were able to pour our sample into that. You can see I'm pouring liquid nitrogen into the bath, and our sample is sitting there. And we poured the simulant sample into the cryopod tray, and then we arranged a little strip heater below the surface and thermocouples near the surface. And then we inserted it and we filled the cryopod with liquid nitrogen and waited until the surface of the sample reached about minus 190 Celsius. And while waiting, we pumped the chamber down and we cooled the plate and the shroud to the regimes that I showed you there that we wanted to target. So we then backfilled the chamber to atmosphere when the sample was cooled enough. And we quickly inserted the tray on the liquid nitrogen cooled plate. And then we pumped down at about 1 millibar per second, because if we went faster than that, we'd blow away the sample. So we still cooled the system at that point, and we stopped at about 2 millibars. And at this point, the surface of the sample was about minus 150 degrees Celsius. And we actually used a sponge to diffuse CO2 that we were going to flow into the chamber so that it didn't blow away the sample surface. So then we flowed in CO2 into the chamber. So you can see the CO2 there. It's connected up to the chamber. And we use this regulator to flow in the CO2. And we tried to hang out at the discrete ranges that I showed you previously. So this work really hasn't been easy. It's really difficult to do, and it's taken a long time to get funding. It's taken a long time to get it right. There's been various things that have gone wrong. So after many years and many months of trying to do this, I was very, very excited to see the next video. So you see a plume. So I wanted to see this for about 5 years. So safe to say that my collaborator, Sarah, came running into the other room when I finally saw this, thinking I had some sort of medical emergency. We were all so excited. You know, she was literally like, "Are you okay?" So I was very okay. So we think that there is translucent CO2 ice on the surface. It's difficult to see. You can see kind of more frosty CO2 ice there, but there may be more translucent CO2 ice at the center, which cracked prior to this moment in the movie. And what you're seeing there is dust escape at high velocity. And we think that what's happened is that CO2 actually diffused into the pore spaces of the regolith that eventually sublimated from within the regolith. So yeah, seeing this was one of the high points of my career so far. Penny Hansen and the folks in the high-rise and CASIS teams have been hunting for plumes on Mars for a long time, so and have never actually caught one. So it was cool to tell them about, you know, that we've at least replicated it in the lab. So here's another example of a less vigorous plume, where you can kind of, and that's the sponge there, if you're wondering what that is. Everyone's always like, what's that yellow thing? That was to stop the CO2 blowing the dust away. So you can kind of see a cracking pattern around. It's not the best quality video. We can kind of see these, you know, cracks happening here before the jet comes out. And then the plume kept going, and it looked like there was one at the back too. And eventually the material above the heater started to crack and sink. So you can see that happening here. And this just keeps going on. I'll show you photos of. So this is the aftermath. And as you can see, the plumes actually reached the top of the chamber. So really justifying the name Dusty. There's a lot of cleaning involved in this work. And then at the back of the top image from the first trial I showed you, hopefully you can see these little channels. And then there was a pit that formed from that plume as well. But when we kept the plume going, it basically erased any surface topography that we formed. So we interpret that CO2 diffused into the regolith pore spaces and sublimated from within it, which is a slightly different mechanism to that proposed for Mars. So also bright halos formed around the perimeter of the heater where the plume was operating. And these are similar to another type of feature in the Kiefer model seen on some fans and spots on Mars. So we interpret that in the laboratory, these halos were triangular crystal frost that formed at the temperatures in the lab of minus 150 Celsius between 2 and 10 millibars. And these observations further support the Kiefer model for the zoo of weird and wonderful features observed seasonally on Mars. So for the next set of trials, we realized that the dust was erasing the surface topography. So we stopped the heater right around when we started to see those cracking patterns. And interestingly, we observed that we got these cracked spider-like morphologies, which developed due to ice cracking within the pore spaces of the regolith. So this is different to the traditional Kiefer model, which involves surface scouring by CO2 gas conduits. So we now wonder if there may be a new variant of the Kiefer model forming cracked spider-like morphologies or pattern ground on Mars, where ice-rich regolith cracks when warmed. In this circumstance, pressure would be released from the substrate, and thus surface scouring would not get a chance to happen. So some researchers have suggested that internal heat stored in high thermal inertia substrate can cause early seasonal plume activity. And perhaps this causes sublimation of interstitial ice within pore spaces in the regolith. And we need to explore this more. Further work will allow us to potentially use morphology on Mars to understand where there is ground ice. So I'm going to leave this side video of the plume up while I talk. So as I said, this work's ongoing. We're going to soon begin further work on phase 2 of the experiments. The next step will be to further refine our methodology and to increase our ice thickness on the MMS simulants and explore more grain size ranges. And of course, then we're going to move on to using a solar simulator instead of heaters to make the situation even more realistic and implement a microscope to try and characterize the ice type. We also want to explore different diffusion depths into the substrate, as well as morphology and activity with grain size and ice thickness, and also possibly more factors like dust in the atmosphere. And in the meantime, we're going to pray that that dust doesn't destroy our pump. If you'd like to read more about our work, it is here. I'm happy to talk about it further with you afterwards as well and answer questions. But just a last few closing remarks. Icy planetary surfaces behave in weird and wonderful ways. Analog lab experiments are essential to understanding how the physics behaves under these regimes. The use of simulants and analog environments is crucial to understanding small-scale processes on icy planetary surfaces. And also cross-disciplinary approaches are very helpful. We have really benefited from teaming up with some of the awesome robotics sample acquisition team at JPL. And if anyone has any questions they'd like to ask me or any hypotheses they'd like to test in the dusty chamber, always happy to talk about it. Please do get in touch. So yeah, thank you. Oh, yes. Yeah, great question. So in winter you get a seasonal CO2 ice layer, and then as it starts to warm up, it starts to crack. And future directions looking at the fracture density in that ice would actually be really useful, because a lot of people ask us, how do you get those really big blocks? Because some of those gullies are 20 meters across, they're huge. So that is definitely something to test. The blocks that I measured, I can't remember, it's so long ago, but they were a few meters. They weren't that big. And so maybe these gullies are widened year to year by smaller blocks continually traveling down. But yeah, they form into blocks through the ice cracking. And then you get ice on oversteepened cornices in the alcoves of the gullies at the top of the dune. And they eventually destabilize and just break off and fall down onto the dune. Yeah.
And let me get you to repeat the question for folks online.
Oh, yeah.
Yeah, thanks.
Yes. It's okay. Great question. So yeah, there's the spiders on Mars, and then the lake stars on Earth, and then that spider-like feature on Europa could possibly all be very different things, but they seem to show, well, certainly the Earth's lake stars and the spiders on Mars have very similar dendritic patterns, but they form by very different processes. I would be very interested to see if we saw features like what we're seeing on Europa on the smaller scale when we get to Europa with Europa Clipper. Because that may be suggestive of near surface brine pool activity. And that's very important because, you know, liquid water near the surface is quite significant, and we should explore those places. So yeah, I would love to see if we see any more patterns like this, and also maybe on icy small bodies as well, other icy moons. We just need higher resolution images. Yeah. Oh, I forgot to.
It's okay. I think you did a good job answering. Other questions? Did you talk at all? How dangerous are these experiments? Are these things where you need to be really cautious when you're doing
Oh
experiments?
yeah, safety is a big thing, especially at JPL. It's very important. This vacuum chamber is a pressure vessel system. And if technically, if it overpressurized, it could become a bomb. So you gotta be careful. I mean, it's unlikely because it has a top hat, it has lots of fail safes. So a top hat is a relief valve that goes off if it happens to overpressurize. We're going to really low pressures, but for some reason, if you were to flow gas in there and forget something, and there was no way for the chamber to open, that could be very dangerous. But the door opens automatically when it gets to atmosphere, so that's great. And we also have a top hat, and we're operating at really low pressures. But then also we're working with CO2 gas, right? That's you've got to make sure that that regulator is working properly, and that the CO2 gas doesn't suddenly pop into the room, because that can cause asphyxiation. So there's lots of dangers associated with it, but we put the processes in place to make sure that they're really mitigated, and got some great safety teams. So shout out to them too. Yes. It's a great question. Yeah. I have not looked at.
If you could repeat the
Sorry,
question.
are the linear features different depending on the slope of the dune? It's a really good question as to how slope affects morphology. There have been some studies done looking at aspect and slope and linear gullies, but I don't think that they've honed in on how sinuous or linear they are. That would be interesting. Yeah. I think it's mostly governed by bumps and pre-existing bumps and twists and turns on the dune that causes the block to change direction. But that would be a good thing to explore. Yes. Okay, yeah. So have there been any proposals to study these with the helicopters on Mars? Not to my knowledge. I started thinking about this recently. I would dream of going to these features and having an in situ study, which I believe you do a lot of work on. So we should chat about that. Yeah, maybe you've set the plans in motion here. I don't know. I would love to see that someday. Because spiders on Mars could be indicative of seasonal dynamics in past climates, and we don't know a lot about that. So, yeah, very interesting. Yes. It's water ice. Yes. Yes. So is the resolution of our cameras good enough to be able to see the spiders? Yes. So at the moment that the image that I showed you was at 20 meters per pixel. So not as high resolution as on Mars, as you can see the smaller spiders on Mars. So yeah, when we get back to Europa, I'm hoping that we might see, well, I'm anticipating that we'll see a lot of weird and wonderful things. So. So are you? Oh, okay. So you're asking, I'm just going to try and repeat the question. So looking at the types of geysers in Yellowstone, would they form? Yeah, I don't know of any work on that relating. So it would again be a very different process. But we see dendritic patterns a lot in nature. You know, even in my pottery class, I can't get away from my work. Honestly, I do pottery to you know, focus on mindfulness, you know, and then I go to the sink and I see the clay, and there's these drainage patterns in the clay. So they're everywhere from lots of different processes, because it's quite an energetically favorable pattern. But yeah, it'd be cool to investigate that more. Yes. Mhm. Okay, so yeah, this question was talking about how when we drill the holes in the CO2 ice blocks, that it wasn't exactly accurate, and if more of a temperature or pressure range would simulate it more accurately. Is that right? Yeah, so good question. Actually, there is a greater temperature difference between the CO2 ice block and room temperature substrate. So that is an even higher temperature difference than what we expect on Mars. On Mars, we expect it to be a more diffuse process where you have this gradual buildup between the ice layer. So that was a very rapid temperature change that we did in the lab. And yeah, great question. As I said before, we aim to use a solar simulator in our next test to try and engender that basal sublimation that sort of gradually happens, that will build up and eventually crack that top layer of ice. Yes. Oh, yeah. This question was asking, do the brine pools form under polar ice caps on Mars, or is it just icy bodies and icy moons? I don't know much about that really. I guess if an impactor were to hit water ice, it depends on the pressure conditions in the region. It all depends on the pressure conditions and how thick the layer would be. I'm not sure we have evidence of a very thick layer where an impactor is hit, that there may be brine pools formed by that on Mars, but I'm not sure. Yeah, it's a good question.
Here, we've got a question that says, what is the temperature / depth profile of the soil in this is in the part of Mars, probably I guess in the part of Mars where you're making your observations. Temperature depth profile of the soil.
On Mars or in the lab?
This is in the part of Mars. I think they probably mean in the part of Mars where you're observing these features.
Oh, yeah, I don't know that information, unfortunately. Don't know.
What the temperature depth profile is. No one's ever measured it on Mars.
Yeah, it'd be great to physically go there and be able to measure it.
They tried with the mole on InSight, right?
Yeah,
And that didn't work.
yeah.
They tried to drill down through the soil to measure the temperature profile, but the mole, the drill didn't actually drill. It couldn't, the soil was too loose and it couldn't actually drill down through the soil. So
Yeah, I think it was optimized for different soil cohesion.
yeah, that's right.
As much as I
That's the one attempt that's been made and it was unsuccessful.
Yeah. Yeah, and that's actually an example of the importance of testing drilling and robotics across a wide range of parameters. And people are doing that at JPL. It's very interesting to observe. With Europa Lander, for example, they were that was the mission that was going to go to Europa and land on Europa. We don't really know what the surface of Europa looks like on the small scale. You know, it could have blades, it could be slush, it could be, you know, we just don't know. So they were trying to optimize that system for all different types of ice. So they were making very hard ice, they were making crushed up ice, and that I ended up benefiting from one of their simulants that they used to test in the Lake Star experiments. So.
Wait, did you have a question? I thought you had your hand up earlier. Okay. Great. All right. Well, if there are no other questions, let's thank our speaker again. And join us. There you go. Join us in April. Our April event will be on the second Friday, because what's happening on that Monday? The solar that's solar eclipse. So second Friday in April, folks. Thanks for coming. Have a good weekend.
Thank you. Okay. Yes. Yes. About an hour from Dublin, I think, maybe an hour, 2 hours. Yeah. Okay. No, I haven't actually. No, I haven't done. I only went to the Giant's Causeway the last 3 years. You know, I was like, I need to do all these tourist things.
Your relatives there and all.
Oh yeah, I've went there.
Somebody from Ireland.
Big tie between Ireland and America. Yeah, it's great. Yeah, excited couple of weeks ahead of us celebrating my home country. Thank you. Thank you so much. Thank you. Pardon? Oh, okay. The recent helicopter ingenuity?
No, the signal was the 24. Sorry, that's very funny. You already booked time on that?
I think Titan would be inhospitable, but
You're right.
not sure I'd like to go there. I think I'll pick the moon first. Yeah.
I got a sort of a question that and a suggestion.
Oh,
You mentioned simulating the sun and the surface of the dry ice.
yeah.
It's been observed in a lot of places, not just where dust particles and to absorb more heat energy, the sun creates more clouds. And so I was just wondering if there was any provision in your experimental plan, put a couple of dust particles on the surface.
Great question. That's actually part of the problem. So there's still some atmosphere of Mars, right? So the ice isn't exactly clear. So this time it's clear when more than all of those. The dust still there. Migrate down. It's called self-cleaning.
But when you do the simulation, if you take the dry ice, it's not going to have that. That's
Very, very good. That's something else that might affect the different morphologies of the spiders as well. That you have that mirror stress, sunlight coming in, some of the energy into around the time it's all right down. And then some of the ice that there is ice. So yeah, that's big risk for those. Are those regions where you just found some spots and you don't have to see the spiders? So yeah, so great.
Okay, well, good talk.
Thank you.
Really,
Thank
I learned a lot.
Thank you so much. Thanks. Thank you. Bye. Thank you so much.
Yeah, thank you.
Thank you.
I don't know that much about that. I thought that the ice that on Europa, I'm surprised it's water. Well,
Yeah.
water, but I would have thought it's. But it's really
That's why it's
H2O.
That's why it's of interest. Do you think there's a liquid water ocean beneath the icy crust?
One of the moons does have a methane ocean.
I think that's hiking, yeah. I don't know. I mean, it's obviously reference in the research. Yeah, drive the cars really.
Okay, cool. Anyway, thank you.
Thank you very much.
Your rectangular simulation, you have a rectangular pit,
Yes.
and I'm curious, the ones on Mars with circular, is there a process for plates that break off and get really down to circular?
Yeah, that's a good question. We can see them break up. So you have like, you have some channels where you get these teardrop shaped.
Yeah.
think that it's something,
Oh,
Break off.
Break off. and go on.
yeah, they're brittle and they break up. Yeah, it's a good point. And that's certainly something that we can do out. I didn't, shape it.
Yeah, it's really striking. Your experiment is very replicable.
Yeah, I'd love to do some more in the public stuff. It's been a while since I did that work. It's, fascinating.
Great talk.
Yeah, thank you so much. Bye.